Next, we are going to discuss about the periodic trend of electronegativity. So this is also a upright property. That means along a period, if you go from left to right, the electronegativity value will increase, and along group, if you go from bottom to up, the electronegativity will increase. So first try to understand what is electronegativity, right? Now you guys have already seen, I guess, this rope pulling game. So there are two teams, and both the teams will try to pull the rope in their side. So if this team can pull the rope in their side, and these members comes this side, so this team wins the game, right? Similarly, if this team can pull the rope in their side, so this team wins. So this rope pulling game is the ideal situation that happens in a bond. So in a bond, two atoms are there, but they are continuously pulling the electrons. I will take a pen. See, assume this team is actually team A, okay, and this team is actually team B. Now in between we have a rope. Just call it a bond. Now this bond is consisted of electrons, right? Two electrons. Two electrons make a bond. So these atoms, they will try to pull those electrons towards itself. Similarly, this atom B, that will also try to pull these electrons in their side. So this is exactly how we play this rope pulling game. So this atom is also pulling these electrons in their side. This atom also wants to pull the electrons in their side. Now, whoever will be the stronger, if let's suppose B is stronger, so if B can pull these electrons in their side, so we will say the electronegativity of B is higher or greater than the electronegativity of A. Okay, let's see the definition now. So it is defined as the electron pulling capacity, that electrons in a bond, of an atom towards its nucleus in a covalently bonded molecule. So this AB, which has a covalent bond in between them, they are trying to pull the electrons, and the electron pulling capacity is defined as the electronegativity. Now key points, so there should be a covalent bond to define the electronegativity of any atom, and electronegativity is not an inherent property, so it depends on its surroundings. So if you change the atom B to atom C or atom D or any other atom, the electronegativity of all the atoms will change. Okay. Now this periodic table shows the electronegativity value of the elements, periodic element of all the atoms. Now from this data we can see, if we go from left to right, let's take this lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. If we go from left to right, the electronegativity value increases. Again, you see in this group wise, if we go from top to down, the electronegativity value decreases. So if we go from down to top, the electronegativity value will increase. So these are the electronegativity values of all the atoms. And this is the 3D bar plot from which you can clearly see that electronegativity is increasing along the period, and if you see here, it is decreasing along the group. Now let's see the reasons. What are the reasons behind it? So let's first see the electronegativity trend along period. So along period, what are the factors there? Principal quantum number is fixed. So the number of shells are fixed. Effective nuclear charge increases. I have already shown multiple times that as we go from left to right, the number of proton increases. So that's why the effective nuclear charge also increases and size gradually decreases. So we have same principal quantum number. We are filling electrons there, and the number of proton is also increasing. As the number of proton is increasing, the effective nuclear charge is increasing, and size is also gradually decreasing. And as we have more and more electrons, the electron-electron repulsion also increases. But this is a minor factor. We can ignore this. So considering all these factors, we can say that electrostatic attraction of nucleus towards bonding electron increases along the period. So the electronegativity also increases. So I will draw it here. You see, this is the nucleus of atom A. Oh, sorry. And this is the nucleus of atom B. So here the principal quantum number is fixed. So the number of shell is fixed. It will have same number of shells, but you see the size is smaller. As we go along the period, the size becomes smaller. So if you form a bond between some another atom, uh, let's suppose atom A. Now if this one is forming a bond with atom A and this one is forming a bond with the atom A, now if the electrons are here somewhere in between the bonds, you can see the electrons of the bonds will be much closer to this nucleus compared to the electrons of these bonds. Okay, for example, if we see these electrons here and these electrons somewhere here, so these electrons are actually much closer to this nucleus because it has high effective nuclear charge and small size. So if the size is small, that time the electrostatic attraction will be more, and that will attract the bonded electrons, that will attract towards itself. So that's why the electronegativity will also increase. That you can see from this atomic number versus electronegativity plot. So as you go from lithium to fluorine, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, you can see the electronegativity is gradually increasing, or sharply. You can see electronegativity is sharply increasing here, right? So similarly, if you go along period, as the size shrinks, the electronegativity increases. Now let's see along group. What is the effect that is playing role along group? So if we go from top to down along the group, the size of the atom increases. Now size of the atom increases means the electrons, bonding electrons, will be much uh, farther from the nucleus, right? For example, let's see this atom, and let's take another atom. Now as you are going from top to bottom, the size of the atom increases, the number of orbits also increases. Now if you make a bond between another atom A and here another atom A, so these bonded electrons are actually much further in this case, whereas these bonded electrons will be much closer to this atom. So this atom having smaller size, it has more electronegativity. Now in this case, in this atom, it is down to the this atom. So so in a group we are going from top to down. So the number of orbits is increasing, number of orbits are increasing. As a result, the size of the atom is also increasing, and these bonding electrons are placed far from the nucleus. So this is the nucleus, and these bonding electrons are placed far away. So that's why the electronegativity decreases along a group. Now here is one more point, that effective nuclear charge slightly increases, which acts in the opposite direction, and it's a minor effect. Now if you see one this element, fluorine, then chlorine, then it might be the bromine. So these elements show that as you go from top to bottom along the group, the electronegativity decreases. But there are some exceptions, and the exception lies in the D series. So 3D to 4D electronegativity falls slightly, but 4D to 5D electronegativity increases due to lanthanide contraction. So along the group, the electronegativity actually should decrease, which is happening from 3D to 4D. That electronegativity is slightly decreasing, but from 4D to 5D, the electronegativity is actually increasing because of the lanthanide contraction. So for the lanthanide, because of the lanthanide contraction, what happens? The F electrons and D electrons, they are having lesser shielding power. So the nucleus, and that is attracting more to the valence electrons, and because of that the size also contracts, and as the size becomes small, now the nucleus of the atom is closer to the bonded electron, and that's why it can pull the bonding electrons towards itself, and because of that reason the electronegativity will be higher. Now now we will try to remember the electronegativity order of the first 12 elements. So this is very helpful actually, and I always remember this in many competitive exams, or during practicals. Many times you need to remember that which element is having higher electronegativity. For example, if I draw pH3, you need to take a few seconds to realize that which one, either the phosphorus or hydrogen, which one is having higher electronegativity, which one is having plus charge and which one is having minus charge, right? Similarly, if I draw methane, CH4, it will take you some time to realize or to remember which one will be positively charged and which one will be negatively charged. Or in case of borosilicates, that is also you have to remember, or you may need few seconds to remember which atom will be positively charged, which atom will be negatively charged, and that you can decide based on the electronegativity order. So the element which is having higher electronegativity, that will form minus, negatively charged. For example, if there is a bond between oxygen and chlorine, so O will be minus and chlorine will be plus charge, because the electronegativity of oxygen is higher, so it will take the electron and it will become O minus, whereas chlorine, which has lesser electronegativity compared to the oxygen, so that will become plus. So for that reason, it will be handy to remember the electronegativity order of first these 12 elements. And I always remember these first 12 elements. There might be some more metals in between in these places. here or somewhere here or somewhere here, somewhere here. But those metals you may not need to know those things, but these 12 elements we need to remember. Yeah, so one more thing, that there might be some more metals in between here, but for our practical purposes, for remembering these 12 elements, we need to remember. Or even if you want to remove this first word, you can remove. So electronegativity order of these 12 elements. Now how to remember? So uh, you have gone to a Xerox shop, and in the Xerox shop you have to make photocopy of some important documents, and then you saw that your friend Firoza Osman's brother is there, and he is secretly copying some photos of girls. So how you can remember? You can remember Firoza Osman's clever naughty brother is secretly copying hot pics both sides. So you went to the Xerox shop and you saw there that Firoza Osman's brother is there. He's also copying something, and he's very clever as well as naughty. And that brother is secretly copying hot pics both sides. So he's photocopying some actress models and their photos with bikinis. So you have to remember Firoza Osman's clever naughty brother is secretly copying hot pics both sides. From this Firoza, you can remember F stands for fluorine, this one. From this Osman, O stands for oxygen. From this clever, Cl, then nitrogen will come, and from the brother, bromine will come, and from this is, I will come, iodine. Now in this, secretly this sulfur, this first S is denoting the sulfur. From the copying, carbon, and what is he copying? He is copying hot pics. So from the hot, H stands for hydrogen, P stands for phosphorus. Both side, both B stands for boron, and in this side, this Si stands for silicon. So you can remember Firoza Osman's clever naughty brother is secretly copying hot pics both side. Or if you know the meaning of Fokla, I remember like this also. Fokla naughty brother is secretly copying hot pics both side. So in Bengali, Fokla means someone who doesn't have teeth. So he has lost many teeth. That's why we call it Fokla. So from the Fokla, you can remember these first three atoms, fluorine, oxygen, and chlorine. And then naughty brother is secretly copying hot pics both sides. That is same as of the above. So this is the easier way in which you can qualitatively remember that which atom is having higher electronegativity compared to the other atoms. So this is a qualitatively you can remember. You don't have to remember these values, so quantitatively it is not needed, but it is necessary to remember it qualitatively, that which atom will come first. Now let's talk about Pauling's electronegativity. So the electronegativity periodic table which we saw earlier, that is actually based on Pauling's electronegativity. So it originates from the concept of valence bond theory, VBT. In a covalent bond AB, the ionic forms also contribute. The contribution depends on the electronegativity difference between A and B. So these two atoms which are forming a covalent bond, so inside their covalent bond they also have some ionic nature. Now because of the covalent ionic resonance, the actual bond energy is always greater than the hypothetical 100% covalent bond. So as I mentioned, if there is a bond between two atoms A and B, so the bond is having some portion of covalent bond and some portion of ionic bond. So that is called covalent ionic resonance. So some part is coming from the covalent bond, some part is coming from the ionic contribution. So that's why, because of this ionic resonance, because of the presence of this ionic nature, the actual bond energy, which is EAB, that is always greater than the hypothetical 100% covalent bond. So this difference gives the measure of covalent ionic resonance energy. So what happens? the actual bond which is having higher strength, if you take that and then subtract the hypothetical 100% covalent bond between A and B, the amount whatever you will get, that represents the covalent ionic resonance energy. So how you can write? You can write this covalent ionic resonance energy delta is equal to actual bond energy minus energy of the corresponding 100% covalent bond. So this delta AB represents this covalent ionic resonance energy. That is actually EAB, the actual energy, minus EAB covalent, which represents 100% covalent bond. So this EAB covalent can be written as this geometric mean. So this is the geometric mean of these two. To understand this, first we have this molecule A2 and we have this molecule B2. Okay. Now if you break these two bonds and if you break this bond and if you break this bond and then if you join this A and B, so this energy of this AB will be actually equals to this value, square root of energy of AA multiplied by energy of BB. Okay, so we can write this value in term of this energy of 100% covalent bond between AB. So if we put that, we get delta AB is equals to EAB minus under root of EAA into EBB. Now Pauling suggested this 100% ionic character in AB bond is actually proportional to the difference between their electronegativity, that is proportional to chi A minus chi B, and that is also proportional to square root of covalent ionic resonance energy or delta AB. So from here we get that chi A minus chi B. This chi is the symbol of electronegativity. So electronegativity of atom A minus electronegativity of atom B is actually square root of delta AB. That means if we take the square root of this covalent ionic resonance energy, we get the electronegativity difference between those two atoms. Now this chi A minus chi B, whichever is greater, you can take that. If electronegativity of B is greater, you can take chi B minus chi A. Okay. So if we put the value of this delta, which is this value, we get chi A minus chi B is equals to this equation. So here delta is in EV, electron volt per molecule. So from there we observe that chi A minus chi B is proportional to under root covalent ionic resonance energy of delta AB. Okay, so chi A minus chi B is equal to under root delta AB, and here delta was in EV per molecule. Now 1 EV per molecule is equals to 96.5 kilojoule per mole. So we can convert this value from EV per molecule to kilojoule per mole. We just divide it by 96.5 and eventually we will get 0.102 square root of delta AB. So here this delta value is in kilojoule per mole. So this delta is the covalent ionic resonance energy. And from there, if we take this value in the left hand side and we square it, then we get delta AB is equals to 96.5 into chi A minus chi B whole square. So this is the one equation that you have to remember, this one, and also this one, chi A minus chi B is equals to 0.102 square root of delta. Here delta is in kilojoule, and also you have to remember this one, here delta in EV per molecule. Simply if you just put 0.102 before this term, you will get delta in kilojoule per mole. And similarly, you can convert this EV per molecule to kilocalorie per mole using this factor. So if you just divide it by 23.06, you will get chi A minus chi B is equals to 0.208 square root of delta. So here delta is in kilocalorie per mole. So these three things, these three formulas you can remember, and from here if we just take this factor in the left hand side and then square both the sides, we will get delta AB is equals to 23.06 chi A minus chi B whole square. So these formulas you have to remember, and I will erase all these things. You can take a screenshot of this. You can pause the video and take a screenshot. Now we will discuss about different type of electronegativity. Earlier we observed Pauling's electronegativity. Now we will discuss about Mulliken's orbital electronegativity, which is represented as chi m. Now Mulliken said that electronegativity of an atom is orbital dependent, and electronegativity of an atom is related to both ionization energy and electron affinity. So Mulliken suggested that chi m of atom A is equals to half of the summation of IEA, means ionization energy of A, and electron affinity of A. So this is in EV per atom. So you can again convert this EV per atom to kilojoule per mole. You have to just uh, divide it by the factor 96.5, and you will get chi m, or the Mulliken's orbital electronegativity, is equals to 0.0052 IE ionization energy of A plus electron affinity of A. So here this ionization energy and electron affinity, those are in kilojoule per mole. Similarly, you can convert this formula in kilocalorie per mole by dividing by this factor 23.06. If you divide it, you will get chi m is equals to 0.0217 ionization energy of A plus electron affinity of A. So here ionization energy and electron affinity, they are in kilocalorie per mole unit. Again, I will remove all those inks. You can pause the video and take a screenshot. Now let's see the relation between Pauling's electronegativity and Mulliken's electronegativity. So the relation is given as chi p, means the Pauling's electronegativity is equals to 0.168 times of this ionization energy plus electron affinity of the atom and minus 1.23. So if we subtract this 1.23 from this ionization energy and electron affinity value, and then if we multiply it with 0.168, we get Pauling's electronegativity. Now this can be converted into Mulliken's electronegativity. This IE plus EA, and we know half of IE plus EA is equals to chi m. So you can just convert it to chi m, and ultimately you will get 0.336 chi m minus 0.616, which will give 0.336 chi m minus 0.2. So this is the relation between Pauling's electronegativity and Mulliken's electronegativity. And even some scientists proposed that chi p and chi m should be related like this. Chi p is equals to 1.35 times of square root of chi m, and then you subtract the value 1.37. So any of the values, both the formulas you can use to relate the Pauling's electronegativity with Mulliken's electronegativity. Now let's see some other important facts. So electronegativity is also orbital dependent, and the sequence for the normal orbitals is actually ns greater than np greater than nd greater than nf. So ns is having, so s orbital is having more electronegativity compared to the other orbitals. That because this s orbital lies closer to the nucleus. Now let's see the sequence for sp hybridized orbitals. So for the hybridized orbitals, the sp orbital is having higher electronegativity compared to sp2 and compared to sp3. Now let's see some examples. For example, if you consider carbon atom, so in case of only p orbital, the electronegativity value is 1.74, whereas when it is sp3 hybridized, the value is 2.52. When it is sp2 hybridized, it is 2.8, and when it is sp hybridized, the value goes to 3.34. So as we can see, as the s character increases, the electronegativity also increases. So if we see here, s character is 0, here it is 25%, here it is 33%, and here s character is 50%. So as the s character increases, the electronegativity of the element or atom also increases. Similarly, in the case of nitrogen, we can see in the pure p orbital, the electronegativity value is 2.52, whereas in the sp3 hybridized form, the electronegativity value is 3.74. In the sp2 hybridized form, it is 4.18, and in sp hybridized form, it is 5.14. So along with that, some additional information that we know, Mulliken's electronegativity is defined as chi m, and chi m is equals to 0.5 multiplied by ionization energy of the atom and electron plus electron affinity of the atom. Now if you just change this plus to the minus sign, so that will give the absolute hardness of atom. So that gives absolute hardness, and it is represented as this this symbol eta. So eta absolute is given as 0.5 multiplied by ionization energy of A minus electron affinity of A. Now let's see some keynotes regarding the electronegativity. So we have observed that electronegativity is actually upright property. That means if you go along period, it increases from the left to right, and if you go along group, it increases from the bottom to top. So that's why it is upright property. Okay, and do not get confused with the term electron affinity. So electron affinity I have already discussed before. So electron affinity is hugely different than electronegativity. Okay, so electron affinity is inherent property of an atom, and it is independent of the surroundings, whereas electronegativity is the property of a molecule bound with another atom and not an inherent property. So let's take an atom A. Okay, so if you make a bond between A and B, and make another bond between A and C, and another bond between A and D, so in all those cases the electronegativity of A will be different. Okay, because its environment is different, it is bounding, it is making a bond with different atoms. Okay, and in Mulliken's electronegativity, we take the first ionization energy and first electron affinity values. The electronegativity is also orbital and hybridization dependent, that we have just seen in the earlier slide. And electronegativity depends on the charge of atom as well. So with the increase of positive charge, the electronegativity increases, whereas it decreases with the increase of negative charge. So this happens because if you increase the positive charge, so the atom will be more and more positive. That means in the atom, it has less number of electrons and it has more number of protons. When it has more number of protons, the electrostatic attraction will be more. The size of the atom will become less. Now when the size of the atom is less, the nucleus will become more powerful, and that will draw the bonding electrons towards itself. So it will try to pull the bonding electrons more and more. So that's why the electronegativity decreases. when we increase the positive charge. Whereas when we decrease the positive charge or increase the negative charge, so that time we are increasing, when we are increasing the negative charge, that time the atom is getting bigger in size. So as the atom is getting bigger and bigger in size, so the distance of bonding electrons to the nucleus is increasing. So that's why the electronegativity value is also decreasing.
Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.